All right, we'll get started now. Just reminders, by the way, I apologize that this looks blurry. So your first exam is on Tuesday. I'm going to give you an announcement regarding office hours for Monday. I'll have a special meeting for Monday evening. It'll be after 5:30 because I have a meeting till 5:30. I'll let you guys know. The lab worksheet due tonight, and then the cam scanning is due tomorrow night. Again, for the cam scanning, I want you to be able to use your camera. I know some of you folks have tablets, but using the camera to scan your exams can be useful in the event you have issues with the Wi-Fi or power goes out or whatever. At least you have a backup. It's always good to have a backup. Okay. Yeah, so yeah, you can airdrop to your phone. You know, Tyler, really what I'd like for you to do is just do the scanning. I mean, for this exercise, I just want you to learn how to scan with your phone. For the exams, if you want to airdrop to your phone, that's fine. And Chase, yeah, I changed the due date of the homework to Sunday. But if you look on Canvas, it still says Saturday, but if you look on WebAssign, it says Sunday. So that's the actual deadline is Sunday. In order for me to update everything on Canvas, I have to upload all the assignments from WebAssign to Canvas. And so I didn't do that, okay? Will there be a tutor for pre-exam? I forget what the tutoring schedule is, Tyler. It's on the homepage of each of the classes. And so this is the reason why I'm having office hours on Monday night so that you can ask me questions regarding the exam. Okay, so Tyler, if nobody is there on Monday, that means we have not been able to hire a tutor for Monday. What you need to do is look at the names of the people below it who are scheduled to be the tutor. So today we have a tutor, I mean, like Tyler's tutoring, okay? But we haven't been able to hire enough people to tutor. Part of it is because of student schedules, okay? So the tutoring is open in those times, but we only have tutors available at the times listed. So yeah, we just got to hire more people. I just, got to find them. So again, regarding relativity review, I'm going to email you regarding the time I'll be available on Monday night. And I don't know about the tutoring that you'll see on Canvas. I don't know about what they're like. I have no idea. Because I've never used them. Yes, something similar to tutor.com. If you go to the page, there's a button for tutoring, and then you ask for a tutor. But I don't know. That's an outside service that's through that the college uses. Yeah, I mean, regarding tutors for us this semester, it's been. We're gonna keep trying to ask. And see if we can get tutors. I mean, they're scarce this semester. Okay. So anyway, Monday night I'll send you an email regarding that. So if you've had 205 with Aviva, or 215 with Harris, with Professor Harris. Basically, when they have you do an exam, you download the exam, work on it, and then upload it. So basically, for us, the exam will be available at 1:55 p.m. You'll download it and print it out. Of course, if you have a tablet, then you won't print it out, okay? And work on the exam and then upload it into the assignment that says Unit 1, Chapter 39. And you got to do it by 4 p.m. Otherwise, it's counted as late.
Okay, so I don't have a printer or a tablet. So for most of my like math exams and stuff, and then also in 215, I just wrote things on a separate piece of paper. Is that acceptable, or do I need to put the actual questions on there?
You can write it on a separate piece of paper. That's fine.
Okay, cool.
Yeah,
Thanks.
that's okay. I mean, I mean, if you don't have a printer or whatever, I mean, that's the way you'll have to go. That's fine. So just I mean, for everybody, just make sure I can read the document. That's why I have the cam scanning practice. Like I said, I had students in the past, you know, if this was my computer screen, okay, I would only see 2 letters from a word on the screen, something ridiculous like that, because it was magnified so much. At least if you submitted me the pages rotated, I'm able to rotate them. But if I can't, you know, if I can't see the whole page on the screen, that's going to be a problem. And I'm not going to accept that. So you just want to make sure that I can see the document. So you can, the cam scanning practice assignment, you could submit a bunch of stuff, as much stuff as you want on there just to practice, to see what your document looks like when you upload it. Okay, it's got to be readable. Okay, so make sure everything's readable.
How many points off will you take if the exam is like a minute late or something, in case we have trouble submitting it?
I have an equation that I wrote down on in your syllabus.
Oh yeah, I remember. Okay.
Okay.
Yeah.
I have a weird equation. It's a decaying exponential. Yeah, and let me know if it becomes a problem. If you have a problem uploading it, first email it to me and then upload it. At least I get a timestamp.
Okay, sounds good.
Okay. As long as I get the timestamp, some sort of timestamps that says you got it done at that time, that's fine. So you can email it to me and upload it. And you know, I really prefer that you upload it because it's much easier to grade, especially those of you who send me PDFs. It's much easier to grade the PDFs on Canvas than it is from an email. It's a pain to read the ones from the email. Okay. And those of you who have accommodations, you'll have whatever your accommodations are. It won't be till 4, it'll be till later time. Okay. We okay? All right. So I want to do one more kinematics problem involving Lorenz transformations. And this is one of those problems that one can spend a long time discussing, and I'm not going to do that. It's related to something called the pole in the barn paradox. This is related to one of the big paradoxes that you'll encounter in relativity, and one can go off on all kind of discussions on that. And my goal is not to do that. Okay, I just want to apply the transformation rules to this system. That's my goal, because I want to keep it brief and I want to talk about momentum and energy. Okay, so let's say we have a truck that approaches the garage. So this is a 30 meter, this is a big truck, okay? 30 meter long truck. Michaela, regarding 210 and 215 tutors, some of the tutors have either had 210 or 215, I can't remember. But I don't know if we've had any tutor that's had both. It's been an issue this past year getting tutors. It's been hard. Sorry, and we apologize for that. Just send an email if you have questions. I'll try to answer. So we have a 30-meter truck. Okay. And we have a garage that's 6 meters long. And let's say the truck is going fast. This is a fast truck. Such that gamma is equal to 15. Okay? And we want to see if the truck will fit in the garage. Okay, we want to see if the truck will fit in the garage. Obviously, you would say, well, that's not going to happen. Okay? So there's a person in the garage. There's an observer in the garage. Wants to see this happen. Let's say the doors are open. Otherwise, the truck will crash. Okay? And I want to consider two events. Okay? First event. Event 1. The rear end of the truck, that's this end, the back end of the truck, and I'm going to show you a picture in a second, clears the front door of the garage. Okay, and I'm going to denote this is the origin for both coordinate systems, and I'm going to say x truck 1 equals x garage 1 equals 0. So when this part of the truck, I'm sorry, yeah, when the rear end of the truck clears the front end of the garage door, this is true, and then this is true. T truck 1 equals T garage 1 equals 0. We're going to say the truck's frame is equivalent to our prime frame. Okay, second event. And again, I'll show you a picture in a second. The front end of the truck clears the rear end, the rear door of the garage. So event 2, front end of truck clears rear end of garage. Okay, so event 2 means this guy reaches this point. So if this is x equals 0, this is x equals 6. And so that means x of g 2 is equal to 6. This is the location of the truck as measured by the person in the garage. We need to figure out how long the truck is in the garage. You might say, well, the truck does not fit in the garage. But according to a person in the garage, the truck does fit in the garage. Okay, according to the observer in the garage, according to the garage observer, the length of the truck is contracted by 15. So the truck is 2 meters long. So that means the truck is travels, the front end of the truck will move from here to here. The front end of the truck will move 4 meters. In fact, the whole truck will have 4 free meters in the garage. Yeah, regarding the PowerPoint, I emailed the PowerPoint to you guys a while back. So I send them through email just because of various issues. I don't put them on Canvas. If you want another copy, just email me. Okay. So if L is 2, how long is the truck in the garage? According to a garage, observer, the truck in garage for how long? Well, event 1 is this, event 2 is this. So the front end moves 4 meters. So we're going to say TG2 is 6 minus 2 divided by how fast he's going, which I'll show you in the previous slide what the I have it there. It's 0.9978 times the speed of light. And so the person in the garage says that the truck is trapped for 13.4 nanoseconds. The truck is in the garage 13.4 nanoseconds, even though the truck is 5 times the length of the garage. Yeah, I'm sorry, nano is 10 to the minus 9. Sorry, Chase. We're going to use the word nano a lot this semester. Now, what about according to the truck? Yeah, 10 to the minus 6 is micros. Okay, what about to the truck? What does the truck say? What is the time at this location? So according to the truck, I'm going to use the Lorenz transformation. T prime equals gamma T minus x v over c squared. But T prime is the truck's reference frame, and I want to look at the second time. So this is T relative to the garage, number 2. This is the final one. And so we want to find the value in the truck frame. So this is going to be equal to T truck 2, which is equal to gamma times T garage 2 minus the location of the front end, the location of the front end of the truck as measured by a person in our frame, the garage person's frame, times the speed of this darn thing over c squared. This number is 13.4 nanoseconds. (13.4 times 10 to the minus 9 seconds. If you do this on the calculator, you will get that T2 is equal to minus 98.9 nanoseconds. According to the truck, this happens first and then that happens second. The order of events has been reversed. And that's okay because there's really no causal relationship between the two. There's no force that's causing one or the other. So according to the truck sees this. By the way, according to the truck, the garage is not 6 meters, but it's contracted by a factor of 15. According to the truck, the length of the garage is only 0.4 meters. Yeah, it is confusing, Chase. That's relativity. In fact, let me make it even more interesting. Let's make gamma 5. Yeah, maybe more interesting means more confusing, but let's make gamma equal 5. Why did I make gamma equal 5? Anybody want to guess why I made gamma equal 5 instead of 15?
Does it make the length of the truck the same as the garage?
Yeah, according to the person in the garage, right? So according to the person in the garage, if you make gamma 5, so if you change this to 5, then according to the person in the garage, this goes from (2 meters to 6 meters. So there is one instant in time where the front end and the back end of the truck are completely in the garage. There's a point where the front end and the back end are simultaneously in the garage. But the truck driver doesn't see that. If you use this equation again for that case where gamma is 5, the truck driver will see that this event occurs first by about 97.9 nanoseconds. Why? Why is it that in one case, the two ends are simultaneously in the garage at the same time, but in another case, they're not? The key word is simultaneous. What do we say about simultaneity and relativity? Two events that are simultaneous in one reference frame are not going to be simultaneous in another reference frame. Simultaneity only exists in one reference frame. If you have two events that are separated in space that happen at the same time in one frame, somebody in another frame will not see them happening at the same time. Of course, you can go on, you know, you can say, well, let's change gamma again. You can make the garage and the truck 6 meters and make gamma 5. And again, you're still going to have this issue. But here's an interesting question I want to look at. What if the truck stops in the garage? Let's go back to this one. What happens if the truck stops in the garage? You must have great brakes. What happens to the length of the truck? Or what happens to the length of the garage? It gets bigger because when you come to a stop, you end up being in the same reference frame. You end up being in the same reference frame as the garage. So the truck will get bigger. So you won't fit. Well, the person in the garage will say, oh yeah, it's not going to fit. How about this? Suppose that I put a brick wall here. Like an infinitely strong brick wall. Yeah, Julia, the truck, so when the truck was moving, according to the person in the garage, the truck looked small because of length contraction. But when it comes to a stop, the truck is going to be in the same reference frame as the person in the garage. And so the truck will actually, both people will agree that they're the same length.
I have a quick question. So, isn't it the only time the truck is going to fit is when gamma is 5 then?
Yes. But let's say, when gamma is 5, when gamma is 5, you're right. But when you come to a stop, the truck is going to be 30 meters long anyway, right?
Right.
Okay. So when you come to a stop, the truck is going to, to the person in the garage, the truck is going to go back to 30 meters. But what if there's a brick wall here? And the truck slammed into the brick wall. Let's look at it from the truck's frame. Okay, you're in the truck. Or actually, you can look at it in the garage frame, either one. If you're in a truck, you slam into the garage, what happens? In fact, if the truck slams into a wall, okay, the back end of the truck will not know that the front end of the truck hit the garage door. And what will happen is the front end of the truck will start getting compressed. Eventually, when the whole thing comes to rest, both people are going to agree that the truck is the same length. Okay. Anyway, it's a problem. It's related to something called a pole in the barn paradox, where someone's running with a pole into a barn. The pole is longer than the barn, and the question is, does the pole fit in the garage or the barn? Okay. So it's just an interesting question. And the thing, you know, when we talk about putting a wall here and the truck crashing into it, if the truck is going so that gamma is 15, it would probably vaporize. I mean, that thing's really going fast, okay? But we're using this example as to, you know, what happens relativistically. There's a lot of interesting problems, a lot of interesting things you can come up with this example. You'll see people write pages and pages on this. Okay. All right, so I just wanted it's just something for you to be aware of, and just another application of the Lorenz transformations. So I want to talk about really two more topics and they have to do a momentum. Since the you didn't get the wall thing, Michaela?
Yeah, so like, so I just don't understand what's the point of like putting a wall there. Is it just to explain that it's gonna eventually come to a stop and they are gonna be in the same frame, or?
Yeah, they'll be in the same frame. But the other thing too is that to realize is that the front end when the front end collides, the back end still doesn't know that happened.
Right.
So it takes time for that information to go to the back of the truck, which means that objects can't be rigid. Relativity demands that object can be rigid. When you were taking 205, one of the last units you did in 205 is called rigid body dynamics, right?
Yeah.
Yeah, but that's, of course that's an approximation, right, to say rigid body. There's no such thing as a rigid body, perfectly rigid body, because that would mean that information gets transmitted from the front end to the back end like that, instantaneously.
Right.
Okay?
Okay.
So I think these last items that I'm going to talk about in this unit, I think are a little bit easier to digest. And it's on momentum. If you apply the Lorenz transformations to momentum as the way it is defined, momentum will not be conserved in every reference frame. Momentum has to be conserved in every reference frame. Okay, if two objects collide and there's no external force acting on the system, then momentum is going to be conserved regardless of what reference frame you're in. Of course, if you go from one reference frame to the next, you have to use a Lorenz transformation, not a Galilean transformation. When you did these problems in Physics 205, in your first physics class, you probably did some momentum problems in the center of mass frame. That's where you use the Galilean transformation. And you did that because momentum momentum is conserved no matter what reference frame you're in. But when we're dealing with objects going at high speeds, and we have to take into account relativity, we got to transform between reference frames using the Lorenz transformations. And using the definition P equals mv does not work. We cannot say P equals mv anymore. I mean, unless objects are moving slow. So I'm not going to derive this. I mean, I do have a little bit of a discussion in your notes, but I'm just going to state it, which is usually done in a class at this level. And just because of the time it takes to go through a derivation. So I'm going to state that relativistically, we must rewrite momentum this way. Where u is the velocity of the object relative to the reference frame. Whatever reference frame you defined. Okay? And gamma this gamma is different. That's why I put a subscript u underneath. This gamma is 1 over the square root of 1 minus u squared over c squared. This is the speed of the object in that reference frame. It's not the velocity of the reference frame. Okay? So let me go through some slides because I'm not going to derive this. I just don't have time. And really, you should be okay without me deriving it. Let me get to the equation. Okay. If you write momentum this way, then conservation momentum works in every reference frame. What do you mean that the U is like V prime? Tyler? U again is the velocity of the object relative to the reference frame. So if I take a ball and I throw it, U is the speed at which I threw it. Okay? I'm using a letter U instead of a letter V, that's all. I use the letter V for the velocity of the reference frame. Okay? I don't want to, otherwise, I'm going to have a V for a reference frame. I'm going to have a V for the velocity of the object. You're going to have subscripts all over the place. Imagine three-dimensional motion where the reference frame is moving in 3 dimensions and the object is moving in 3 dimensions. How are you going to write that down? Okay, so that's why we use 2 different letters. Otherwise, it'll be really confusing.
Is there a difference between the U with the vector on top and the U and the U squared and the square root?
Well, U dotted with U is U squared. Right? I mean, that's what U squared is, the dot product of a vector with itself. It's the square of the magnitude of the velocity vector, right?
Oh, okay, so they're both the same value, it's just the top one has direction.
Yeah, well, remember, this is squared, this is not.
Oh, okay.
Right, this is a vector, this is a scalar. All right, this is the magnitude of the magnitude of the velocity vector squared. That's really what it is. Like when you use 1/2 mv squared in the kinetic energy, the v is the square of the magnitude of the velocity vector. So this is associated, so this has a u in it. Just remember that. Okay. When you write this down, I would always write the subscript u. Our textbook doesn't do that, and I really think it's confusing. Even on the slide, you don't see the u there, but there should be a u there. Okay. And you actually don't see the distinguish, you don't see textbook distinguishing them until like you take a junior level class, and it's kind of annoying. Now, what about kinetic energy? Again, I'm not going to derive this. The equation for kinetic energy has to be modified also to take into account relativistic effects. Why? Because momentum has a different expression. If you set up, I mean, force is dp dt. So the work done, of course, you know the work done equals the change in kinetic energy. That still doesn't change. But you want to take the force dotted with a displacement. Okay. But this is the same thing as dr over dt dotted with dp. And what's dr dt? Where's the velocity of the object relative to the frame? So if you go through and integrate this, you will get an expression for the work done on the object, which I have in the notes. I'm just going to state the final answer. Okay? So using the work energy theorem, you can derive an expression for the kinetic energy of the object. This is what Einstein did. And so what you get is an equation that looks like this. The kinetic energy of the object We're assuming the initial kinetic energy is 0 when we're doing this derivation. The kinetic energy of the object is gamma sub u minus 1 times mc squared. Okay. This is Einstein's famous equation. Well, this is kind of Einstein's famous equation. Okay. So the kinetic energy is written this way. The kinetic energy is equal to gamma mc squared minus mc squared. This term is called the rest energy. This term is called a total energy. Okay, same gamma of mu. So when you do work on a particle, if we call this the mass of the object, if you do work on a particle, you change its mass from m to gamma times m. When you do work on a particle, you change its energy from mc squared to gamma sub u mc squared. It also is reflective of a change in mass. Mass changes. So Einstein put mass and energy on equal footing. Now, granted, you're not going to see this effect in mechanics. You only see this effect with things involving high energies, with quantum particles, stuff that's going really fast. Okay, you can get mass getting converted to energy and vice versa. So the mass of the object changes. Okay.
Professor?
Yeah.
So actually, yesterday I read it somewhere. They said that the mass does change an original concept, but now they say that the mass does not change.
Yeah, there's always been a debate about, well, the rest mass doesn't change. I mean, this never changes. I mean, that's a invariant. But how we interpret this has people have always argued about how we interpret it.
So is this actually like, because there is gamma multiplied by m, so does the mass increase?
Yeah, and I'll show you, let me show you, I'm going to go through some examples where the mass gets converted into energy and mass changes.
So if the mass gets converted into energy, shouldn't the mass decrease rather than increasing?
Well, it depends. If you have, suppose you have two particles that experience a repulsive force. What's going to happen to the particles? They're going to shoot off. You're going to have kinetic energy. That increased kinetic energy is reflected in the bigger total energy, bigger mass. Now, if you have, let's say you take a proton and a neutron, and you push them together somehow. Okay? You push them together. So they form one particle. This has a mass m sub p. This has a mass m sub n. The mass of the new system is going to be less than the sum of these two. This particle is called a deuteron. So this is what I was going to talk about anyway. Okay. The mass of this is less than the sum of these two. So where's the missing mass? Where'd it go? It went into stored energy, the energy of the system. The energy that's required to hold us together reduces the total energy of the system. Okay. If you take a mass and you stretch it, you're increasing the energy of the system. You've done work. You've added energy to the system. And so the mass will increase. The energy that's stored in a spring is reflected in an increased mass of the system.
So there is an increase in energy, but the amount of the material does not change, right?
What do you mean the amount? I mean, it does in this case. I mean, the amount of mass does change.
No, like if you say that two things collided and then they go in opposite directions and you see an increase in their mass, right? Because there is an increase in their kinetic energy. So, but that increase is not due to an increase in mass, really, right? Because the amount of material in each did not change.
Yeah, and it depends on the interaction, though, right? I mean, it depends. We can't just say, I can't make a definite conclusion about one way or the other. In the example that we're talking about, yes, you're right. So let me do some examples and then we'll come back to this, okay?
Okay.
Okay. All right. So just summarizing, the kinetic energy of the particle is gamma mc squared minus mc squared. And E total is gamma mc squared, which is equal to the kinetic energy plus the rest energy. And what doesn't change is the rest mass or the rest energy. That's the same in every reference frame. If you add energy to a system, the mass will change by an amount delta E over c squared. Independent of the kind of energy that's added or removed. And so what this does is we don't have to worry about work done by this force, work done by that force, whatever. We just say that the mass changes. Total energy is conserved. So instead of writing potential energy plus kinetic energy in conservation of energy problems, I just write this expression. Okay, that's the total energy a particle has. Now, what happens to this expression at low speeds? Gamma sub u, what happens at low speed? So if you do an expansion, you guys have done this in Calc 2. And these are things you can look up in a table. If you expand this for, you'll get that gamma is approximately equal to 1 plus 1/2 u squared over c squared. And the reason why I stop here is because this term is going to give me the first non-zero term. So the kinetic energy then for low energies is going to be, for low velocities, is going to be this. The ones cancel, and I'm going to get 1/2 u squared over c squared, m c squared. The c's cancel out, and 1/2 mu squared. And so I get the classic expression for kinetic energy. Okay, granted, I'm using a letter U instead of a letter V, but this is the classic expression for kinetic energy. So for low energy, this agrees. Okay. Now when U goes to C, this thing becomes infinite because it means it takes an infinite amount of work to reach the speed of light. So in a conversion of rest energy into kinetic energy with the corresponding loss in mass occurs in radioactive decay processes, and then things involving a gain in mass, you see them in nuclear fusion processes. When you fuse two atoms together or two particles together to get a bigger one. Okay. Now, if I take this expression for P and then rearrange it, okay, if I take this expression for P, I'm going to write it explicitly right in terms of U, and then I rearrange it, I can write the total energy as shown in the slide. So let me write all my equations. I have P equals gamma mu. Then I also have the total energy, which also can be written this way. This is the rest energy of the particle, and then this is the energy associated with the momentum of the particle. Now, I want to say something. What if we have a particle that doesn't have mass? Do they exist? Do particles with no mass exist? Yes, they're called photons, particles of light. And there's some particles that are very light that we can almost ignore their mass, called neutrinos and antineutrinos. And so when the object has no mass, objects that have no mass essentially go at the speed of light all the time. Okay, no mass, but they go at the speed of light. So if they have no mass, this term is gone, and the energy is just P times C. So energy of a photon is just P times C. Or if you're doing an antineutrino or neutrino, which is one of your homework problems, you're going to assume this is zero. You can approximate this to be zero and say P times C. In fact, we don't know it. No, we don't know yet the mass of the neutrino yet, so people are still trying to figure that one out. So you're right, just P times C. Okay? And the value E squared minus PC squared has the same value in every reference frame because that's the rest energy of the particle. Okay, so I want to do collision problems. Suppose I have two identical particles, they collide together. They collide and stick together. Did you do this problem in mechanics? Two particles, same mass, equal but opposite velocities. What happens classically?
They stop.
They stop, right? Because what's the total initial momentum of the system? Isn't it zero?
Mm-hmm.
So we have two objects going this way. Same mass. From classically, you have from conservation of momentum, m times u to the right minus m times u to the left has to be equal to m plus m times u final. And so u final has to be 0. That's going to be true in this case too. I mean, u final has to be 0 afterwards. My total initial momentum is 0. The only difference is I have to write my momentum this way. Okay? Everybody okay with this? You guys remember this, right? This is called, what's this kind of collision called?
Inelastic. Completely inelastic.
Completely inelastic collision, right? Okay, it's a complete inelastic collision. All the kinetic energy of the system is lost. Okay, let's do it relativistically. We know it's going to stop, so I don't have to write conservation of momentum, right? I don't have to do this. That's for this one. This has to be 0 because the total initial momentum is 0. So we know U final is 0. Okay? So we know, it's obvious, U final is 0. Okay, so whatever I end up with, the particles are not going to be moving. All right, at the end, the particles are not going to be moving. So I want to write the total initial energy equals total final energy. Did you do this for inelastic collisions? You conserved energy in the problem? Do you remember having to do conservation of energy in an inelastic collision problem? We gotta be careful what I said, right? Did you use conservation of kinetic energy in an inelastic collision problem? The answer is no. Right? Kinetic energy is not conserved. Kinetic energy is not conserved, right? But I'm looking at the total energy. This equation takes into account energy losses due to production of heat, sound, whatever. So I can use it for any kind of collision. I do not have to specify whether or not the collision is elastic or not. So let's do total initial energy. Each particle has an initial energy gamma sub u times its initial mass times c squared. Isn't that true? The total initial energy I had is the same for each particle. They're going in opposite directions. Total initial energy of the first particle, total initial energy of the second particle. What about at the end? What's the total energy of this particle? Well,
MIC squared.
I'm sorry.
2 times.
Yeah, but what's gamma in this case? What's gamma at the end?
1.
1, right? Because it ain't moving. So I can write, and it depends on how you want to define this. I can write this as a single composite particle, so I don't have to write the 2 here. But in the problem, usually this problem, they just stick together. You still treat them as separate objects. So what's my final mass? It's gamma some epsilon sub I. So if the particles are moving very fast, the final mass is not going to be the same as the initial mass. In fact, the final mass is greater than the initial mass. And the reason why is because kinetic energy is converted into thermal energy. Okay? So included in is that there's thermal energy being involved there.
Professor,
Yeah.
how is thermal energy related to mass here?
Well, again, we're making them equivalent.
Okay.
We're putting them on an equal footing. We're saying mass and energy are the same thing. The system gets hot, right?
Yes.
Okay, so that's extra energy within the system. The internal energy of the system has increased.
Yeah, that is the thing. Like the energy increased, but mass is not energy, right?
Mass is what?
Like mass is like it is some material that you have. It is not energy, right?
Yeah, I mean, I understand what you're trying to say, but it's hard to grasp this, that the masses, that your masses are completely different. And
Like
let me, and it's going to again, it's going to depend on the problem, but that's how we look at it. Let me just do the problems with the nuclei. Just let me
one
get to that.
thing.
Okay?
Yeah.
Okay. I just want to get to that. If you want to calculate the change in energy of the system, you just take the final energy minus the initial energy. So if you take 2 gamma, the final energy minus the total initial energy, I'm sorry, not the final, the change in rest energy, the change in rest energy. This is going to be the change in rest energy. Okay, and let's assume V is small. We already showed you what this ends up being, right? With the approximation for small v. That's the total change in kinetic energy of the system. This is the total loss in kinetic energy of the system. This is what you would get when you do it classically. But when I do the problem classically, I don't talk about conservation of energy because I can't conserve kinetic energy. Okay? Now, just to make sure that this works, you can, and I think I'm going to have to skip this because of time, but you can do the problem in the reference frame of one of the particles. So let me do that real quick. I just want to say something about this, and this kind of worked out completely in the notes. But suppose I do the problem in this person's rest frame. How fast is the other particle coming towards me? Let's say I'm sitting on this particle. How fast is the other one coming towards me?
Do you?
It's not to you. Remember, we got to do a Lorenz transformation.
Oh yeah. Okay.
So this is what I'm going to do. If I'm in the reference frame, both these speeds are relative to the Earth, right?
Mm-hmm.
Okay. So if I'm sitting here, moving to the right, the Earth is moving to left. So with velocity, minus u. If I'm sitting on the particle, the Earth is moving away from me at minus u. And this is coming, this is moving, in the Earth's frame, this is moving to the left at minus u. So if I want to use the velocity transformation, If I want to use the velocity transformation, that's a prime, that's a prime. In this equation, u sub x prime is minus u. V is, oh, this is a plus, sorry. V is minus u. And then the denominator is 1 plus minus u over c squared. So I'm stationary and this thing is coming at me at this speed. Okay, well, the magnitude of this is the speed, right? Does that make sense? That's how you find the velocity of one object relative to another object using Lorenz transformation. I kind of wanted to point that out. And so we're going to use conservation of energy. So conservation of energy, basically, I'm stationary because I'm sitting on the particle, so I only have rest energy. This guy is coming towards me, gamma initial, m initial, c squared, and afterwards, now gamma initial is this. But this is this guy. So let me make this bigger. This equation that you see, this is the speed of the particle up there. Okay, now look. Don't I have to, I have to conserve momentum too to solve this, right? Isn't that true? I have to conserve momentum to solve this? The answer is yes. But I'm not going to do that. Look, if in our frame, if we're sitting here and we're watching these two collide together, the final velocity is 0, correct? Mm-hmm. If that final velocity is 0, what is the velocity? What is that 0 velocity relative to this frame?
Zero?
If I'm sitting, if I'm sitting on here and the Earth is moving away from me at u, isn't the final speed of the system going to be u? Mm-hmm. Isn't that true? Everyone's having a hard time with this. Two objects collide together, they stick together, and they come to a stop. But if I'm moving with speed u relative to those particles, it's going with speed u. Look, two particles collide, and they stick together. And I'm on a bus moving that way 40 miles per hour. Are those particles going to look stationary if I'm going at 40 miles per hour?
No.
No. It looks like those particles are going to be moving away from me at 40 miles per hour, right? Mm-hmm. So the final speed is, in this reference frame, the final speed of the two particles moving together is going to be u. It's going to be the speed of the reference frame. Does that make sense, Chase? All right, I'll say it again. Two particles collide. They come to a stop because they have equal mass and they're going in opposite direction. We're standing here. We know it's not going to move. But somebody who's in a bus moving away from it at 40 miles per hour is going to say, no, it's not stationary. Those particles are moving away from me at 40 miles per hour. Isn't that true? They're stationary relative to us, but not relative to the bus. Okay, so that's why I'm saying the final velocity is just going to be u. And then you can go ahead and do the math and you can show you get the same answer. So basically this slide, all I'm saying is that you can do the problem in a different reference frame and get the same answer. Okay? The reason why I went through this is because of the fact that I want to show you that energy or momentum are conserved in every reference frame. Okay. And if you want, for your amusement, you can do this problem again at low velocities. So let me talk about. I'll try to do this example last. And I apologize. This slide didn't show up. The table didn't show up in your notes. I'll send you a new set of notes with this showing up. So the rest mass of any composite system is always less than the sum of the rest masses. So like I said before, if I take a proton and a neutron and I combine them to form something called a deuteron, you can use that or the letter D. Now you'll see that this mass and this mass don't add up to this mass. Now, when we do problems in relativity, look, the mass of the proton is 1.67 times 10 to the minus 27 kilograms. The mass of the neutron is about the same. I'm not going to write the next decimal place. Okay? Its rest energy is going to be, let's say the rest energy of this is 1.67 times 10 to the minus 27 times the speed of light. This is a small number in joules. Okay? This is a small number in joules. So I'm going to divide, I'm going to use a different set of units called the electron volts. So I'm going to divide by 1.6 times 10 to the minus 13 mega electron volt, joules per mega electron volt. And so this comes out to be, the rest energy for the proton comes out to be 938.3 MeV. So since the mass of the proton times c squared is 938.3 MeV, then I can write the mass of the proton is 938.3 MeV over c squared. That's how you write the mass of a proton. This division is because I defined a different unit. I defined the unit as 1 mega electron volt is 1.6 times 10 to the minus 13 joules. 1 electron volt is 1.6 times 10 to the minus 19 joules. It's just another unit. So that I can write everything this way. Okay? So I'm going to write the masses this way instead of this mess. So having said that, if you take the mass of the proton as 938.6 MeV over c squared, and the mass of the neutron is 939. Forget the number. 6 MeV over c squared. The sum of those two values, what does this come out to be? What's the mass of the deuteron? Did I add those right? The mass of the deuteron? 1875 point, I think I wrote it down wrong. The difference, notice, these two masses don't add up to that. Do you see that, Raftesh?
Yeah.
They don't add up. Where's the missing mass? It goes into the binding energy of the system. It takes energy to bring them together.
So the mass gets converted into energy?
Yes.
Okay. All right.
Okay. So the mass gets converted into energy. So the difference, and you might want to double check my math here.
It was 938.3 for proton, right?
Oh yeah, it's 0.3. That's my mistake. Okay, now I'm happy. The difference is 2.3. Basically, this number times c squared is the amount of energy that's required to keep them together or to pull them apart. That's the binding energy. So there you have mass being converted into energy. Okay, so I just did this problem. Okay, same thing if you do a nuclear fusion problem to form with tritium, you can talk about how much energy is released. In this particular example, energy is released. You actually combine masses. And let me get my numbers. Can't look for my, trying to look for my values. Okay, so we're going to take a tritium atom and a deuterium atom and form a helium, which happens in stars. So we're going to take, this is basically a hydrogen atom with 2 extra neutrons. This is a hydrogen atom with 1 extra neutron in it. It's an isotope, it's called an isotope of hydrogen. You blast them together in a violent collision and you get helium plus some other particle. And energy is released. Okay? So, if you look at this energy, this mass is 3727.41. And then this energy, this mass is 939.6. This ends up being a bigger number than what you started with. This number is bigger. Okay, this number is bigger than this. So what that means is energy has to be released in the process. So energy is released. How much energy is released? Well, you got to take this minus that. And I'll write it down without the units. So I'm going to do this. This is the amount of energy released per fusion. Well, I got to multiply this by c squared. The difference in mass times c squared is this much energy. This is an enormous number. That's why fusion bombs are so powerful. Thermonuclear weapons are so powerful because of this number is so big. This is per atom. This is how much energy is released per atom. So imagine if you have Avogadro's number of atoms. Okay? That's about 1,000,000 times greater than any chemical reaction. Why was it a subtraction? Well, as opposed to what, Chase? If I want to find a difference between the two, what would I do? I mean, this is what I started with, and I ended with this. So I want to find a difference, right? No, that's what's nice about this. I'm just looking at energy released. I mean, I'm just taking the final energy minus the initial energy. If it's positive, energy is released. If it's negative, then mass got somehow converted to energy of the system. Yeah, it is kind of cool, but this is a scary number. Okay, that's very big. It's about 1,000,000 times greater than any energy a chemical reaction can release. That's right. Okay, let's see how much time I have. I want to decide. I only want to do one of the two because of time. I did have a whole lot of examples. This one's easy. I'll do this one, and then I'll make a video of the other one. Okay. I'll make a video of the other one and have it to you, so you have another example to work with. I really don't think these problems are very hard, because it's the same thing: conserve energy, conserve momentum. Conserve energy, conserve momentum. I'll make a video of the other one, and you can watch it. Okay, so a proton and an antiproton, what does that mean? They collide. This is the antiparticle of this. Means they have the same mass but opposite charge. They slam into each other and produce two photons. Let's say they were at rest to make the math easy. I put them right next to each other. And they somehow interact and they annihilate each other. The mass gets converted to energy. How much energy does each one of these have to have? That's the question. Well, if they were at rest, both of these, so I'm going to do initial energy equals final energy. And really it's the sum of these two, right? So this is not moving, so all the energy I have is the rest mass, or the rest energy of each one. And these are photons. Okay? So I have the energy of the first photon plus the energy of the second photon. Now, how do I know whether or not they have to be the same or not? How do I know what is the relationship between E and 1? So I produce two photons, two quanta of light. Light is released. How do I know whether or not they're the same or different? Well, what else do I have to conserve? What's the other quantity I have to conserve? I'm conserving energy and what else? Not mass. What are the two things you learn to conserve in Physics 205?
Momentum.
Momentum. So momentum has to be conserved. Every problem you do here, you have to consider conservation of energy and momentum. Now, sometimes the momentum conservation leads to something easy. So how much momentum did I have at the beginning if they were at rest? 0. So I started with 0. So the sum of the initial momenta has to be equal to the sum of the final momenta. So if 0 is equal to the momentum of the first one plus the momentum of the second one. Well, if they add up to 0, what can you say about the momentum?
It's conserved.
Yeah, I know, but what can you say about how do you compare their values?
Equal and opposite.
That's right. So P1 equals minus P2. So when these things interact with each other and they annihilate these two photons, which are quanta of light that always move at the speed of light, they have to move off in opposite directions. So that means that they have the same energy. Why? Because remember, I showed you another equation for the total energy. This is another way you can write the total energy. And photons have no mass. So the energy of a photon is momentum times c. Okay? So these two are the same. And so these two are the same also. So the energy of each photon is going to be equal to the rest energy of the proton or the antiproton. So the energy is going to be 938.3 MeV. So you got to conserve energy and momentum. Every problem is the same. Any collision problem, conserve energy and momentum. Okay? That's all you got to do. You conserve energy and momentum. I don't know how many times I have to say it, but that's really all you got to do. But the energy we're talking about is total energy, not kinetic energy. In Physics 205, when you did elastic collisions, you conserved kinetic energy. Here you're conserving total energy. Because relativity puts all forms of energy at equal footing. That makes sense? Okay, so I've covered everything I need to cover. I just need to make that video, just give you another example. Any questions, concerns? This one? Kathleen? Okay, so one of the slides I showed earlier, I had this equation. What was the equation? Oh, yeah. Okay, so I had this equation earlier. If you rearrange this, and I don't want to go through it, but I hope you believe me, but you rearrange this, solve for u squared over c squared. Okay, and then do some more rearranging to derive it. It comes from this. It comes from taking this equation and rearranging it. Okay? I mean, I didn't derive the equations here just because I didn't have time, and I don't know if, because this is just an algebra thing. Usually when there's no time, I won't derive an equation. But if you want to, for fun, you can try. It's not easy, actually, to do this. There's a trick you got to do when you invert that equation. There's a trick you have to do to get this form, because you have to multiply something by c squared over c squared to actually solve for this. It's a little tricky. Okay. Other questions?
In the classical physics, like when we conserve energy, why don't we consider the rest energy of the particle as well? Like we say it is kinetic plus potential, and if there are any non-conservative forces.
Well, I mean, if you saw the approximation, well, the rest energy hardly changes. You can ignore it. It cancels out. I mean, if you write the kinetic energy like this, if you write the kinetic energy like this and then you do the expansion, the first term is a 1. Right? We had these two terms cancel out, this goes away.
Okay.
So the rest energy essentially doesn't change. That's why. It just disappears.
In a previous question where we did proton plus neutron and it gives you deuteron, right?
Yeah.
For that, how come the charge was not conserved?
Because I didn't write down the charge of the deuteron.
Oh, okay.
Yeah,
Is it
and
plus?
that was, people write it like that a lot. You're right, charge should be conserved. Let me go back. Or let me just write it down. Yeah, because I wrote this down. Which has a positive charge. Neutron has no charge. In fact, I do this. Atomic number and the charge. I'm sorry, atomic mass and atomic mass and the number of protons. Yeah, this is ionized. When I'm dealing with a particle such as, in these kind of problems, when I'm dealing with a particle such as a deuteron, its mass is 4,000 times the mass of electron. I'm ignoring it. That's why I didn't put a plus sign there. And a lot of times physicists don't, even though they should.
Is it the same as if you have a deuterium and you ionized it?
If you had a deuterium and what?
And you ionized it, is that deuteron?
I'm sorry, I didn't hear the last part.
If you have like a deuterium, then you ionize it, is that deuteron?
Yes. Okay. It's a deuteron ion. It's just an ion. That's
Okay.
all. It's still called deuteron, but it's just you can say it's a deuteron ion. Right? Just a hydrogen atom. If you take the electron off, it's still a hydrogen. I mean, it's just a hydrogen ion.
Mm-hmm.
Right? Same thing. I mean, there's even this is not working very well. Hydrogen molecule and the deuteron molecule. I mean, it's the same. I mean, if you ionize them, then they just become ions. Other questions? What? I can take a couple of homework questions for a few minutes if you have them. If not, that's fine.
I have a question.
Okay.
It is on the lecture that we did today.
Okay.
So when we did the problem where two masses were coming towards each other and Earth was there, we said that the velocity of the Earth is negative u, right?
Yeah, because the Earth is moving away. If I'm sitting on the particle, the Earth is. So let me draw the picture. Here's a coordinate system fixed to the Earth. Okay? And here's the particle. You're sitting on it. You're going this way. Isn't it true that if you're sitting on it, this thing is moving away from you?
Yes.
Okay, that's why I used minus u.
Yeah, so it was minus u when the particle was moving, but when the two collided, it came to a stop. Then the Earth is not moving relative to the particle, right?
The Earth is.
Like first the particle was moving, so therefore we can say that the Earth is moving relative to the particle.
Yeah, but the reference frame doesn't move. The reference frame is still moving, right?
Isn't the reference frame attached to Earth? Or no?
We were doing in this particular problem. The reference frame was moving with the particle. In order for us to, when I did the velocity transformation, I assumed that I'm sitting here and moving with the particle. That means the Earth was moving away from me. Now I have to be in an inertial frame, so I have to keep moving at the same speed.
Okay.
Okay? Other questions? Oh, let me see. So number 3, Jacob. Okay, so number 3. Let's see. Okay, so and I'll do it generically. You want to figure out, the twins problem. So, how long does? Well, let me write it shorthand. Time for Speedo's trip. So you got to figure out the time required for Speedo's trip relative to the Earth. So let me call this T sub s, okay? All right, just distance over time. Is that okay, Jacob? Then, how long or how much older is Speedo after trip? Even though it might take this many years, which is the distance over time, Speedo, because Speedo's moving, Speedo's clock runs slower. So gamma sub s because this involves speedo's velocity. So this is how much speedo aged. Then you do the same thing. Time, I'll use a different color. Time for Goslo's trip relative to Earth, which is T sub g, which is basically, again, the distance over the velocity of Goslow. Okay, and that's the distance divided by the velocity of speedo. So maybe I should write that down. Okay. Then you got to figure out how much older is Goslow after the trip, which is going to be T sub g over gamma sub g. Now, here's the thing. When speedo gets there first, he's now back in the Earth's frame, but he has to wait for Goslow to arrive. So how long must speedo wait for Goslow to arrive? Well, that's going to be T sub g minus T sub s. What should I call that? T wait. So, speedo's aged this much, and speedo has to wait this much for Goslow to arrive. So the total time that speedo aged is this plus this. The total time that Goslow aged is this. So you take this minus the sum of these two, and they'll give you the answer. Does that make sense, Jacob? And is that what you did, I guess? So what you want to do is take, I'll use a different color. Oops, that's a G. Is that okay, Jacob? Okay. So I don't know if it's if you did this and it's not working, then some sort of round off error. So tell me, Jacob, which part is not clear? Right? This is how long it takes for speedo to get to the planet. This is how long speedo ages. Okay. But I guess my question is, did you do it that way, Jacob? And I know this is an idealized problem because you're coming to an instantaneous stop in this problem, okay? Other questions? Number 7. Okay, let me look at number 7. Okay, so electrons are accelerated to 19 GeV. GeV is, oops, that's not 7, that's 8, sorry. The total energy of a proton is 6 times its rest energy, so gamma is 6. So you're saying E proton is 6 mass of the proton, C squared. So that means gamma is 6. Oh, you got that part? The second part? Oh, Chase got, I'm sorry, I got mixed up. So are you okay with that, Chase? Yeah, that's it. And then you know, just so you got to find out U is, right? You got to solve for U. Once you know that, yeah, so you just do it that way.
Can you hear me, Professor? Can you hear me?
If you write the mass in MeV over C, if you write the mass in, Chase, if you write the mass as MeV over C squared, you do a lot less work. Because most students, they're going to do this the brute force way. And it's a lot less work. Really what you need to do is solve for U over C. Once you get U over C, then the problem is you do very little work. Other questions? The last problem was going to take a little bit of algebra for you. Especially the last problem, part D. Because you got to take the derivative of the expression for A. Okay, so that might take a little bit of work. Yeah, if the number, what number is that one? 15? Number 15, part D, is going to take you some work. Because you're gonna have to, because you want power, right? Oh no, you want acceleration. And so when you take the derivative of the equation in A, which is kind of messy, it'll take a little bit of work. Okay, good, Jacob. So, do I have a different version? Oh, number 16, I'm sorry. Yeah, it's number 16, sorry, not number 15. I can't see the number on this one page because it's stapled. Once you start working on the energy problems, they're not too bad, because every problem is just conserve energy, conserve momentum. I mean, it's stuff you did in physics 205. but just with a little twist with the gammas in them. Okay? What you did in 205 was you conserved momentum and kinetic energy. Here you're conserving momentum and total energy. That's the difference. And then the form of the equations, you're going to have gammas in them. Okay? So what I'll do, I'm going to make a video of the other problem. And I'll talk through it because I want to show you, I want to talk about different ways to solve it in that video. So you get one more example. I think the more examples you get, the better. And I think once you've done that example, once you see that example and you look at the practice test, those problems shouldn't be that bad. Okay. And I know the stuff from the beginning, from the first 3 lectures is harder. That I understand. You're welcome, Chase. Anybody else? Okay, so I'm going to end it here. So I'll let you know when on Monday I'm available. And I apologize for, the fact that we don't have enough tutoring. We'll look into getting more tutors. All right, so have a good weekend, everybody.